Okay, so shall I start? I didn't get a notification if it's recording or not.
So yeah, we can start.
Okay, great. Let me hide that. Okay, so my talk today is going to be on a new material that has been fabricated in 2018 called twisted bilayer graphene. It extends the kind of 2008 revolution about graphene based on some theoretical predictions in 2010, 2011, and it was realized experimentally in 2018. The outline of the talk is briefly I'm going to talk about normal graphene, and then I'll start talking about twisted bilayer graphene. Then I'm going to get into the theory of the system, starting with band theory, where we go from the things that we know from quantum mechanics, like the single particle band theory or energy levels, to crystalline band theory. And then, in order to talk about some of the progress that's been made theoretically in modeling this system, I'm going to talk about the Hubbard model and Hubbard-like models and discuss what they've accomplished so far and what is still left to be explained. And one of the many exotic features of twisted bilayer graphene that I'm going to focus on in the talk is in section 4, where I'll talk about superconductivity, and more specifically, the unconventional nature of the superconductivity, and in that why it is a very appealing alternative to the kind of previously unconventional superconductors, which are the super high temperature. And finally, I'll talk about some future challenges, some other things that can go on, as well as summarizing the other exotic features of twisted bilayer graphene that I didn't mention. I'm just going to focus on superconductivity because that was the first big reveal. And so one of the names that we'll be seeing in the references a lot is Pablo Herrera. He is the PI of the group in 2018 who isolated this system. And his description of graphene is to think of graphite as kind of a deck of cards. So you can think of a layer of graphene stacked up is just one of the single cards being stripped away from the stack of graphite. And so one of the neat things about graphite, and the reason why it was such a catalyst for a lot of really cool theory, was that the electrons in graphite, and we'll explain this a bit more later when we get to Dirac cones and things like that, the electrons in graphite actually behave as if they are ultra-relativistic particles. Ultra-relativistic, it's still, not maybe 1/300th, I believe, is the figure I remember, the speed of light, but still, the fully relativistic Dirac equation ends up making an appearance in condensed matter, and that's unexpected. That's something you would expect to see in high energy at Brookhaven or something like that, but it's indeed something that comes up in condensed matter, and so I'll be discussing that and why that's the case shortly. By the way, please interrupt at any point if you have questions, or you can keep them to the end. It's entirely up to you. And so one of the really cool features of taking two sheets of graphene, so taking it's kind of like a deck of cards, but twisting the sheets a bit. If you are to twist the sheets in a specific angle, what is called the magic angle, 1.1 degrees, as you can see in this figure, something happens where the stacking of the carbon lattice, graphene is just a hexagonal lattice of carbon atoms, and the carbon atoms line up in a specific way, and I'll explain more of these dark patches later on when I get to the Hubbard-like models, that they make what's called a Moire pattern, and that's a pattern that wasn't there when it's just a single layer, and so it's just a word that describes this kind of pattern that's happening. It's been used in art and found in nature and mathematics. It's kind of an emergent pattern that forms that is distinct from single layer, and that's a resounding theme that we'll be seeing, that twisted bilayer is indeed much different than regular graphene. As kind of preview of what's to come, two of the very special things that are not present in normal graphene but are in stacked and twisted graphene are superconductivity, specifically unconventional, as well as a Mott insulator. And so a Mott insulator is something that cannot be naively described by band theory. Again, we'll talk about that more later. And it is described, so if you imagine a band theory description, this material ought to be a conductor. So we have Fermi level that is in between one of the bands. And so the conduction band and the valence band overlap. And so it makes sense that electrons are free to conduct. However, one thing that is neglected in this picture is an interaction strength between lattice sites. So at each lattice site, based on the Pauli exclusion principle, there can only be a spin up and a spin down electron. And so including those, we actually get a splitting. So an energy gap forms. And so this band gap leads the material to actually behave as an insulator. Now let's get deeper into this band theory.
Sorry, I don't understand. May I ask a question?
Yeah, absolutely.
Conduction and valence bands overlap. What does this mean?
Yes, I'm sorry. I should have included or not described this figure too much and waited until I got to the band theory section. So let me quickly go to explain that and what I mean by that. And so if you think about a single atom, in quantum mechanics, you can think of discretized energy levels. And when you think about a kind of the orbital, electron orbitals as they go out, the highest occupied is the valence band. But of course, when you talk about just a single atom, it's more a valence level. And so the conduction level would be a level that is able to be excited to. And so applying a voltage, for instance, an electron in the valence band can jump if it's a proper energy gap. Like if the energy supplied is enough so that it can jump because of the discretized quantum mechanic allowed energy levels, then the electron in the valence band can jump to the conduction band. This is much more clear in solids. So here we have a kind of one of the cells of graphene. This is 6 carbon atoms linked together. And so here the idea of a level is more generalized, or is generalized to the idea of a band. So here these are conduction bands and valence bands. And so going back to this picture, this idea here is that the energy level of well, we can even simplify it to the single atom case, where this energy tells you that there is enough energy for the electrons in the valence band to jump to the conduction band, because they are right next to each other.
Sorry, I don't understand. According to terminology, the whole first, the upper band is conduction band, because it can conduct electricity. And the one which is completely filled is valence band.
I see. So
you cannot say that half of it is valence and half of it is conduction. It's either conduction or valence band.
I see. So it doesn't make sense to say that there's half of a band filled. It's more that the valence band is the conduction band in that case.
So the upper band here is the conduction band because it is half filled.
I see. Okay. Okay. So that's a terminology that I didn't know. Okay, got it. And so one of the weird things that happens in standard graphene is that these bands actually form a very specific pattern. And so for instance, these bands come to kind of a singularity. And so this is known as the Dirac point, where the Fermi velocity equals 0. And so these linear lines here of the conduction and valence band end up meaning that the electron is behaving as if it's massless, and hence that behaving as if they're relativistic particles. And moreover, another thing that this implies, because of how close these are, they're touching at kind of like a singularity, if you will, an infinitesimal voltage, or just a very small voltage, allows the electrons in the valence band to conduct to the conduction band. And this Dirac cone picture in single layer graphene is even more unusual or novel in twisted bilayer graphene. So what happens if you here ignore the fact that there are two sheets on top of each other? And so between two sheets there, of course, if you aren't naive, there's some repulsion between where the electrons are and if they can hop between sheets. And so as you allow for that repulsion, there is this kind of energy gap between where the Dirac cones interact. And so as the twist angle is decreased, those cones get closer and closer together, so the two layers are overlapping. And I'll get more into this in the Hubbard section, why this so-called flat band condition, as you'll see on the next slide, why this flat band condition is really the epitome of what's going on in twisted bilayer graphene. It explains why there is this Mott insulator type behavior. Here's a better figure as you decrease the twist angle. So here, this is just a slice of taking two of the Dirac cones of two of the layers and imposing it next to each other so that it appears as if, so even though this looks like it is just the figure from before, this is actually Dirac cones from two different layers, and as you decrease, it's just isolating one region, so a localized region. And this flat band is known as the flat band condition, where the perhaps it's better to wait until the end of the Hubbard model section, where this can be explained in terms of a diminishing of kinetic energy, and so much so that it practically vanishes, and a very small interaction, which we'll call potential energy, ends up dominating the term, leading to strongly correlated physics. So let me get to that. So back to this slide, we have one of the things that was realized shortly after superconductivity was that there is indeed a strongly correlated phase in twisted bilayer graphene, and one of the ways that this has been modeled is through something called the Hubbard model, where you imagine taking a lattice and including the principle, or the Pauli exclusion principle, that if there are two at a lattice, there is some repulsion between the two. And so when I said that the flat band condition is kind of the idea that between the two layers, the hopping term, so this hopping term is movement, so kinetic energy is in the form of hopping between lattice sites. And when I say hopping between, I mean an electron hopping between lattice sites. And so the idea of the flat band condition is that there is no hopping, and that the kind of insulating material, the insulating phase is evident in the fact that no hopping is occurring, and so there's kind of like a locked up behavior, and that's exactly characteristic of a Mott insulator, where at first, with conventional band theory, you would think things are moving around, and then when you include this interaction, there's actually a gap forming, and so things aren't moving around, and it is effectively an insulator. One of the weird things about this is if this were present in any kind of generic system, it wouldn't be so miraculous. But the idea that excites people is that this strongly correlated Mott insulator-like phase occurs directly next to a superconducting phase. And we'll get to that in the next section, but that is a key feature of unconventional superconductivity. I'll explain why that's a key feature of unconventional superconductivity. So if you think of this, perhaps this would have been a nice slide to explain that conduction valence band idea, that if you were to think of a superconductor based on these three options here, where would it go? Well, it's kind of a superconductor, so naively you would think that it goes on the right-hand side, right? It's a superconductor, so you would think it would be as far away from an insulator as possible. And so that's one of the keys to unconventional superconductivity, as we'll see in phase diagrams in future slides, that having these right next to each other is something that is unlike the conventional, or where these three BCS superconductivity were awarded the Nobel Prize for understanding ordinary or conventional superconductivity in the 1970s. Something weird that happens with unconventional superconductivity is that they are right next to each other. And so that naive assumption that a superconducting phase would be as far away from an insulator phase as possible, that's indeed not the case with cuprate high-temperature superconductors. And cuprate high-temperature superconductors are our best hope at the moment for, I think there are some iron materials as well now, but these are the highest of the high-temperature superconductors at the moment. And so conventional superconductors, their superconducting phases occur at very, very low temperature scales. And the hope, obviously, is that eventually we can continue to fabricate high-temperature superconductors that eventually reach room temperature. And so the dissipation of energy reduction that we would get would, kind of revolutionize how the world works, really. And so the excitement about twisted bilayer graphene, how this relates to this, is that these cuprate high-temperature superconductors are ceramics that need to be doped, and at least on paper, twisted bilayer graphene is simply two sheets of a single atom, right? It's just carbon atoms, a single atom sheet of things on top of each other with a twist angle. I'll talk a bit more in the outlook about why that might not be so easy, right? However, using experimental and simulation, the phase diagram of twisted bilayer graphene has been shown to be nearly identical to that of the cuprate high-temperature superconductors. And moreover, some of the research that's been going on recently, actually in 2020, another of these viewpoint articles that we all looked at to determine which talk we wanted to give, there was one by Subir Sektiv about strange metal phase in twisted bilayer graphene. And so this is relatively recent, that these two were kind of the first mapped out region of the phase diagram, and just this year it was realized that there's also a strange metal phase. And so that's another exciting thing, that something that wasn't well understood in the cuprate high-temperature superconductors, that this is indeed another reason that twisted bilayer graphene has been exciting.
For a question?
Yes?
So how did they see strange metal? So what was the observation?
I believe it had to do with testing the resistivity of the material. And so one of the key features of a strange metal phase is that the resistivity scales with temperature. And so that is something unlike a normal metal, where something called the Fermi liquid theory would apply. Here, in a strange metal, Fermi liquid theory breaks down. And so you cannot describe it with the standard theory from before. And one of the key, something that is definitely not a Fermi liquid is something that scales with temperature, or has a resistivity scaling with temperature. And so if, I'm not exactly sure, I can't give a definitive answer, but if I were to read the paper on finding the strange metal phase in twisted bilayer, I would anticipate that is the feature that they found that made them say that. There are so there's another route to studying strange metals, and that's by a field called holography. It's kind of applied string theory, and there's another term. This is kind of the idea is called Planckian dissipation, I'm not exactly sure how this applies in strange metal behavior, but I know that those two, so Planckian dissipation and resistivity scaling with temperature, are the two key features of a strange metal.
Okay, I just one comment that I encourage everyone to ask questions during the talk. It's what we are here for. Okay, yeah, please, thank you.
And so, this is all very exciting, but even for Cooper high temperature superconductors as well as twisted bilayer, this Hubbard model, while it naively looks simple based on what I've described in it, it is still a strongly interacting system. And so when that flat band occurs and the kinetic energy practically vanishes, even a very small potential energy can lead to strongly correlated behavior. And so it is not solvable in any way, shape, or form. In some very special cases, it is solvable. But for a physical system like twisted bilayer graphene, while these Hubbard-like models have been able to confirm that this flat band vanishing of the kinetic energy is indeed linking to these Moire patterns and all the neat, strongly correlated physics that's going on, that's about all that's been able to be concluded so far from these Hubbard-like model theoretical models. There are some new developments in making continual models more rigorous, and so the ultimate goal of these theoretical models is to go from first principles, thinking of a Hamiltonian and the dynamics, to reproducing a kind of phase diagram that you can get from experiment. And so that is, in a nutshell, the challenge that is still ahead, going from a first principles theory to reproducing and explaining all the rich phase diagrams that occur in these systems. And so I mentioned why Cooper superconductors are difficult to work with, and at least on paper, why a twisted bilayer graphene is easier to work with. And so, at first glance, this does seem to be the case. You can think about this is a quote from the PI who fabricated the material. When you think of a Cooper high temperature superconductor, growing those ceramics as well as doping them could take a very long time and is expensive. I don't have any sort of thing to back up if it is cheap or not to manufacture twisted bilayer graphene. Of course, it's to be taken with a grain of salt if the researcher who's potentially going to be winning a Nobel Prize for this likes to talk up how cheap and helpful this material is. But I think nonetheless, the idea is that, and so here let me briefly touch on some of the things that go against the idea that it's very simple to do these systems. And so his group started working on this in 2010 after a paper by Bistrischer and McDonald in 2010 and 11, which kind of opened the door to these types of things. It wasn't until, as I said in the very beginning, 2018 that this was fabricated. And so it was many years of trial and error with getting things to very low temperatures, maintaining very low contamination, as well as the last key here was that in 2018, one of the graduate students in his group came up with a device that enabled very high pressure and able to keep it enabled the angle to be more specifically tuned. And that's was apparently something that was giving them trouble for 7 or 8 years. And so it's not clear to me if indeed it is as quick and cheap to manufacture these systems as some of the ones who work on it state. But from a theoretical standpoint, it is very alluring because the system is indeed cleaner. It's a single, right? It's a single atom sheet of graphene on top of another single atom sheet of graphene with an angle in between them. And so looking at all the other things that go into a high temperature superconductor, the doping and the other elements in the ceramic, it is indeed a cleaner system. And so that, from a theoretical point of view, it is indeed still very interesting to study these. And the main thing I want to leave you with is that we only talked about superconductivity. And so there are actually many, many more very cool physics that has been observed in these high temperature superconductors, notably the topological physics of things called churn insulators have been indeed found in these twisted bilayer graphene. And a churn insulator is essentially something that is a kind of like a Mott insulator. Like, it's, once you include the interactions, things lock up. And so in the center of the material, or kind of in the bulk of the material, it is an insulator. However, a special thing happens on the edges that the surface states can conduct. And so it's kind of an insulator wrapped with a conductor. And a very weird topological techniques are needed to explain this theoretically, and having a new system that is, again, a clean system and exhibits these topological features is very exciting, as well as what I mentioned before. And one of the phases of the high temperature Cooperate superconductors that is currently being studied and has been being studied for quite some time is the strange metal phase. So where band theory fails with this Mott insulator, recall, a standard band theory would say that this is a conductor, whereas we know that if we include interactions between the electrons, it is actually an insulator. And so in an unconventional superconductor, also the conventional DCS theory of superconductivity fails. And now we have a strange metal phase where we know that Fermi liquid theory fails. And so theoretically, this system, while also being exciting experimentally because it enables us to think more about unconventional superconductors and potentially getting closer to a modern day realization of it, there's also a ton of theoretical mysteries. And so that's at least what I'm most excited about with this material, and I hope I've contaminated you with my excitement about it. And so some of the references I used throughout the slide, and I also just wanted to thank Professor Ivanov, as well as Professor Kano and her graduate student Erin for a lot of discussions on this topic, as well as many pointers to the references that I used here. And so I'll go back to the table of contents, and so maybe that would help with some questions.
Questions?
Yeah, Jason, I was wondering if you could just talk a little bit more about that device that the grad student, if you knew anything more about it, that the grad student has created. I think the Yao.
Yes.
Yeah, because I don't know. I was just looking at that figure, and I was just like wondering, like, what's going on here with this.
So yeah. Let me try to let's see. I can do it kind of with my hands. I wonder if there's some kind of drawing feature on, but of course it would be kind of silly with the mouse. So the idea that this graduate student came up with is, imagine a substrate is prepared. It's kind of like a tool bench, kind of. So you have this substrate that you prepare, or really grow, because you can grow graphene. So you grow graphene on one of the substrates, and the idea, I believe the key word that they have been using in popular science is kind of a cut and paste technique. And so half of the graphene is sliced, and another substrate with, if I remember the element correctly, I think it was boron nitrate, comes up above the material and kind of picks up half of the graphene. And by using these substrates, there is a lot of, and that's what this device is. It's a kind of pressure provider. And so using the pressure on these substrates, it enables you to have a ton of control over the angle. And because the angle needed in things like this is very small. I mean, imagine trying to visualize what 1 degree looks like. Let's see. It's practically, non-existent. And so getting the angle right is indeed what they've been doing for the last many years. And so when this graduate student came up with this device that enabled the pressure of the two steps, the pressure to control these substrates so accurately, and then once the twist angle has been established, it is lowered down, and then the stacks are formed. So the two sheets of graphene on the first substrate and on the boron nitrate substrate are put together. And the idea behind what substrate to use is that in some sense the graphene wants to stay attached to the substrate more than it does to itself. And so that's how the cut and paste, the cut part of the paste works. You can rip the graphene apart before putting it back on top. I understand that's a very hand-wavy way to talk about this, but yeah, that's a good point. I should have included some better figures for the cutting and pasting.
Yeah, no, I was just interested. I mean, it was like there's like a lot going on. I was just like to see more about it. Yeah.
You mentioned doping, changing the amount of charge on these, and of course the tricky thing about doping a ceramic crystal is you have to get whatever is balancing the charge in and out of there. How is doping accomplished in this thin film geometry?
That's a great point. So if we go to, I believe so on kind of a phase diagram of Hubbard superconductivity, it's usually hole doping versus temperature, and on a phase diagram of, although this phase diagram isn't the best, it's still hole doping. I believe the factor that plays a role in doping is something called the Moire filling factor. I can also send you there is an article that has kind of a figure of the Hubbard superconductor phase diagram overlaid on a twisted bilayer phase diagram, and it shows the correlated phases sandwiched between these superconducting phases, and that's where I'm remembering this. So I'm recalling a figure that had a x-axis of Moire filling factor, and I can't exactly explain that. I remember that word, like that was the word on the x-axis, and I don't know how that's done, because the whole idea is that this happens at the twist angle, and so the idea is that if you were to change the twist angle, things wouldn't occur anymore, and so doping needs to happen in some other way. And so I think your question is a good one, and it's one that I should know the answer to. So figuring out what this Moire filling factor is, and I will absolutely send you the figure that I'm talking about.
Yeah. So actually, if you go to one of your last slides, I think I can help to get you in the right direction. It was a picture. It was an illustration of a device, some leads and sort of a schematic illustration. There it is. There it is. That's the one. So I think what you have here is this film that's on the electrodes, and then there's another electrode called the gate, which produces an electric field and can change the amount of charge that's in the device. So that's interacting with the bands, the nature of the bands that are that come from the Moire angle.
Okay.
That's the really exciting thing about this is that there are two independent controls. One changes the shapes of the bands, and one changes the number of charge carriers.
Okay, thank you very much. That makes a lot of sense because the idea of this strongly correlated physics happening is that there is some potential, happening. And so if there's a very small potential, as soon as the small potential happens, there is strongly correlated physics. And so it makes sense that potential is coming from somewhere. And thank you.
So one question that I had is this seems to be an experimental work, but I didn't see too many data. What are the measurements that they took?
And so measurements regarding what features? Like
The breakdown of conductivity, for the mod phase, for example.
Yeah, so I really wanted to focus on the theory of this material. I don't know a ton of, for instance, what happens at when a insulator phase goes to a superconducting phase. I would have to learn a bit more about that. So
it's not the criticism of your talk. It's just a question that I had because it seems that they went through lots of experimental work to make these things, to set up these materials, and then I guess one would wonder what the quality of the experimental results is that they got with that.
Right. Okay.
Questions?
I ask about charge insulator that you mentioned. So I'm not sure if I'm correct, but the charge insulator phase should break time reversal symmetry, right?
Yes.
So in tested bilayer graphene, what would be the mechanism that one can potentially break time reversal symmetry?
So I believe there are actually 3 symmetries that are breaking in twisted bilayer graphene. There's time reversal. I believe there's some kind of charge and translation symmetry breaking, but I can't say for certain. But you're absolutely right that there is indeed time reversal.
So should this occur at the region that is in the phase diagram? There is an antiferromagnetic phase, right? Should this charge insulating behavior occur there or somewhere else in the phase diagram? Okay.
That's exactly right.
Thank you.
Thank you.
Okay, I think we should actually move on to the next talk. We are a little bit over time already.
Okay, and Jason again.
See you again, yeah.